Hello and welcome to the video. Today I'm going to review Rohde & Schwarz FSC6 Spectrum Analyzer that I have right here, and it measures between 9 kHz and 6 GHz. As you can see, it has a very high portability factor. In fact, you can just take it in one arm quite easily, so it doesn't weigh too much. I would say about maybe 7 kilos. It's also a very budgetary spectrum analyzer in the market. You don't really get the level of quality associated with Rohde & Schwarz for price less than that. Obviously, the main disadvantage of this is the small screen size that can be quite tricky to look at as compared to, let's say, industrial spectrum analyzers that you will see in anechoic chambers there and then. Also, to make this video useful, we're going to look into using this spectrum analyzer to check quality of USB cables. And for those of you who have already seen my how to pass radiated EMC video, you probably already know what to expect from this experiment. Nevertheless, as part of the setup, I'm going to use my near-field probes that go between 9 kHz and 5 GHz. So I've got magnetic loop probe and electric field probe. Also, I'm going to use an audient audio interface to pass the USB signal through the cable, because if you don't have any signal going through the cable, then what's going to create emissions? And that's a very common mistake people sometimes make. They would go to the chamber, connect all the cables, but they will just not click start. And there will not be any applications running on those cables, so there will be no problems. So when you first unbox your Rohde & Schwarz FSC6 Spectrum Analyzer, it's going to look pretty much like this. So there's not going to be anything external to it. What you do need is obviously an RF cable so that you can connect your magnetic field probes. Obviously, you need magnetic field probes as well, and you may also need to purchase a low noise amplifier. I know it doesn't look like a low noise amplifier. In fact, this looks more like a bit of paperwork, and what it is a unique activation code for the low noise amplifier that is actually already built into the spectrum analyzer. The most ridiculous part about it is that the low noise amplifier is already built into the spectrum analyzer, and you just need to buy this leaflet in order to enable it. And what's the funniest bit of all is that you may have to wait for it. So we've got a few options here, and we want to enable the amplifier that we have just installed. And as you can see, the noise floor dropped immediately, which is a really good sign. So now we are ready to actually connect the cables and start measuring our setup. So the first thing we're going to insert the RF input here. It is standard 50 ohm impedance. So as you can see, I didn't change anything there. You have some limitations here, so the maximum input is 20 dBm, which you have to be careful with, so not to actually break the device, and don't try to insert more than 50 volts DC into this port as well. So this is just some basic common sense that you should follow. On the other end, let's get the audio interface and just try to power it in. This is quite convenient because this is a self-powered audio interface, meaning that I don't need a power supply, I just need to plug in a USB cable. Right, and here you go. The audio interface is actually working, and we can now play some audio into it, whatever. And now you can see that the audio is actually playing. So you can see that the buttons are blinking, which is exactly the indication of its loudness. Before we jump into measuring actual cables, let's first of all review some of the basic features that this spectrum analyzer has to offer. The first button we've got is the frequency button. So the frequency button allows us to set, well, guess what? Frequency. So we can either select it based on the center frequency, or we can define a start and stop frequency, and we can also have a little step size, which I don't normally do, but you could just set it to something unusual here, like for example doing step like 2 megahertz steps instead of like the usual 1 megahertz step size. Can't imagine why would you want to do that. Anyway, so the span basically sets your frequency as well, and this time if we set it to full span, that we can see the entire window of the spectrum analyzer, which is from 9 to 6 gigahertz. And with the bandwidth that I have selected, you can see that the update rate is quite slow. But anyway, let's go back to 400 megahertz that we had, and I'm not actually sure where we are anymore, so I'm gonna have to redefine my frequency. Right. Then following that, we've got the amplitude, and the reference level is quite important, because the reference level is what sets the maximum expected level of your input, which in this case is near field probe. So it doesn't really matter in this case. However, if we were measuring something through a low impedance stabilization network, let's say for conducted emissions, then that's going to be an entirely different story. And it's very easy to damage a spectrum analyzer like this by setting inappropriate reference levels. In this window we can also choose different units, as well as ranges and offsets. As well as I showed you earlier, we can here decide whether we want to use our preamplifier or not, and you can see that with or without preamplifier we have very different responses. So typically low noise amplification is necessary to make any kind of decent measurements with a spectrum analyzer. Right, the other thing we've got here is RF attenuation, and I do recommend you to keep the attenuation to 10 dB, which is the standard level, but in this case we also have some automatic low noise settings, for example, that allows us to get the best attenuation for the noise. But in general, just sticking it to 10 dB is a safest setting, because that way you ensure that you are very unlikely to damage the spectrum analyzer. After the amplitude button, we've also got the bandwidth, and the bandwidth is the most important setting that I typically use, because this is the eye of the spectrum analyzer, so this is how it's looking through the world. And basically narrow bandwidth allows you to zoom in on specific peaks, for example, I don't know, like this one here. With a wide bandwidth we're not going even to capture that, for example. So let's give some sort of demonstration. I'll try to, okay. So this is a peak. And now if I'm gonna try to increase this bandwidth, you can see that it becomes really difficult to distinguish it from noise even. First of all, your noise is increasing as you increase the bandwidth because it's not averaging it precisely anymore. And secondly, your peak just becomes a very flat sort of peak, which you don't know really where it's coming from. Might be coming from USB cable, might be coming from anywhere else. But if you narrow down the bandwidth, you can see much better where it's coming from. Right, so you also have a video bandwidth, which basically is a smoothing factor. So the video bandwidth you can set to different value compared to your resolution bandwidth, but all it's going to change is the resolution of the noise in the background. So you can see that it becomes a little bit smoother or kind of random as we increase or reduce it. The next button we're going to look at is the sweep button. And the sweep button basically sets a sweep time, which is related to your resolution bandwidth. So I typically leave it by default value because I am adjusting resolution bandwidth, so I don't need to adjust the sweep time. However, you may have a different preference for doing that. You can also set here some trigger events, which includes external rise or external fall, and the gate settings will allow you to set some precise configuration of that. This isn't particularly useful for EMC debugging as such, but you would use that for your EMC test chamber setup, where you want the measurements to enable automatically and disable automatically as well. That will save you some time. So then we've got in this little box the measurement modes, so that includes some of the fancy ones. We at the moment looking at our Spectrum Analyzer video, which is a spectrum measurement, but we can also look at channel power, occupied bandwidth, TDMA power, and then ACLR. So basically all those things relate to radio frequency measurements of LTE, or when you have a specific frequency that you're transmitting at and you want to measure the transmitter occupied bandwidth, this is where you're going to go. But you have to perform those measurements in an anechoic chamber. Otherwise, this isn't going to be very accurate. And there are some specific standards for channel power as well as occupied bandwidth, which are set by ETSI standards, but in Europe. But this isn't the topic of today's video, so I'm not going to go into detail about it. We can also have a measurement of spectrum emission and harmonic distortion with this spectrum analyzer, as well as AM modulation there. All of those, again, is the kind of tests you would do for your Wi-Fi, Bluetooth, or LTE, or 5G, something that you have a carrier frequency and a transmitter, and then you're gonna actually measure what it's actually doing. For EMC purposes, we typically stick to spectrum, and that's that. Then we've also got a trace window, which you will see me using quite a lot, and the trace window allows us to set different modes for the tracing, which could be average. So if we average it, then it starts and then gets an average of 30 values. We can increase that to make it an average of, say, 50 values. Obviously, the larger the value, the longer it takes to get the average. This is quite useful. As well as you can do minimum hold and maximum hold. So the minimum hold is the trace minimum, while the maximum hold is the trace maximum. So trace maximum is very useful when I'm doing some general scanning around the product, let's say like this. Then I can get a feel of what is the maximum of noise I get from it. Essentially this, for what we're doing, I'm going to set it to clear right, at least for now. Then what else have we got? We've got some limits, so we can set a limit which we can base it on some standard which I don't have loaded, but you could have done. And then this is basically displaying okay, I have some settings for GSM, lower and upper limits, for example, and that just sets us kind of expected values that you should have. It doesn't seem to have any default values for, let's say, EM55432, so I can't really put that on. Then the last button we're going to look at is the marker button, and the marker button is the very basic window that you will get with any spectrum analyzer. It just, what it sounds like, allows you to set the markers on your traces. So if we are looking at this peak here, we can see that this is M1, and the value of it is approximately 222 megahertz. We can now add another marker, and if it has a letter D in front of the marker, that means it's now measuring the difference between two markers. So it's now giving me the result. So if I'm looking at the nearby peak, then the difference between peak 1 and peak 2 is 3.8 megahertz. So this is what D3 tells me. Or I can look for the difference between that and oh god, bear with me, and that peak. So this is about 170 megahertz. So we can select the M1, and now we can move the M1 and see what's the difference from there, and that's about 166 megahertz. I'm not sure what my D2 is doing, it's not even in a frame, but anyway, I can bring it in a frame. Then again, you have some other options here for markers. I don't normally play with this, but it could be quite useful for, like, it depends on what you're doing really. So we can switch between M and D functions just by clicking marker type. And that's pretty much it in terms of functions of this spectrum analyzer. When we looked at the trace windows, we can see that in actual fact it only allows me to select two traces at a time. So I find this the most limiting feature of this model. But of course we must remember this is an entry-level spectrum analyzer, and it's going to have some limitations. This is the most obvious limitation in my opinion. Just like any modern spectrum analyzer, it also has an option to save your data into a USB stick, and you can just do that by clicking the save button, and basically it's giving you an option to select it as either dataset or a screenshot. Another lacking feature of this spectrum analyzer is it does not let you to output your peak values as a table. So for example, if I had 10 different markers on the screen, I wouldn't be able to create a peak table based on those markers. And again, I find it quite limiting because it's something that I do like to do. You can also play with some user preferences, so you can change your screenshot type. You've got some options which we looked at earlier when we installed the preamplifier, and you finally have some instrument setup as well as the measurement setup. Not sure what H copy does. Does it do anything? No. Another interesting feature of this spectrum analyzer is that it's got a power meter mode, which I've never really used before, but this is kind of what it looks like. So I suppose if I was measuring a specific signal, which I'm not, then I could have set its frequency here, and then it would maybe give me a power output. But it's something I haven't really tried doing yet, and I don't think I can do it in my current setup. So we're just going to move on back to the spectrum analyzer mode. And now we can actually start looking at magnetic fields around our USB cables. So let's do exactly that. I have already configured the spectrum analyzer to be in a bandwidth between 100 MHz and 600 MHz. Actually, last time I think it was 200. So let's do that again. So 200 MHz to 600 MHz. And that is so that we can see all the emissions coming from USB signals. The next thing we need to set up is bandwidth, which I see is already set, but just to go over it again. So by default, the spectrum analyzer will start in automatic bandwidth, and we're looking at resolution bandwidth as well as video bandwidth. So the one we really care about is the resolution bandwidth, because this is what is the eyes of our spectrum analyzer, is the basically the width of its window that it's scanning. So when it's scanning is the resolution of that scan. What I tend to do is I tend to reduce the bandwidth to 100 kilohertz, and as you can see, this automatically also lowered down the noise floor because it perceives the noise a lot more accurately now as when it was looking with a very wide window at it. With regards to video bandwidth, it's essentially the smoothing effect of the spectrum analyzer. So it's not going to change the peaks, but what's going to happen is that it's going to have different pattern for noise as we either increase or reduce it. So it's a good idea typically to follow it with the same basically value as you set the resolution bandwidth to. So now we can start looking at the actual cable. And basically, if you remember, it sometimes changes based on your orientation. So I'm just going to rotate my probe 90 degrees consistently. And you can actually start seeing that here. So we have a bit of spike, right? And so what we can do to narrow it a bit more down, we can put a marker on it, and basically this is telling us that the spike is around 217.7 megahertz. So another clever thing we can do about this is we can set our trace measurement to max hold. So basically what it means that now, instead of consistently writing and clearing the value of a trace, the spectrum analyzer is going to take its maximum. And this is what we see in this specific area. So what I can do now, I can go throughout the length of the cable and I will see the maximum amplitude of this signal. So on this spectrum analyzer, when you select a new marker, you have to match out whether it has an M or a D. And basically the difference between them is that D is the delta of the two peaks. So basically what delta tells us is the distance between your M and the spike that you're looking at. So it's a frequency between your first marker and the second position. Whereas your M is your ordinary marker. So what we can do now that we captured this maximum noise coming off this USB cable is that we're going to swap it for a different USB cable and compare. So to do that, let's first capture this trace so that it remains saved in the memory. So I saved some memories and now I have the memory one that I have enabled on the screen, whereas my trace no longer follows the memory. So I can see that now I can just change that to clear right. And you see that the footprint has been saved on the background. Another way we can do this is by actually selecting a different trace, and to do that you just select a trace 2. So now you can see that on a screen we actually have a choice of traces. We can switch between trace 1 and trace 2. But for the object of this exercise, I'm not going to bother with trace 2. I'm just going to save memories of the same trace. And you can do it with different ways on Spectrum Analyzer. So I swapped it for a different cable, and this time it is connected to the my extension box. And we can see that the audio is playing as it's clearly doing its thing, and we can start looking at the waveform now. So again, we can select the trace mode to max hold, and we can now follow the length of the wire to capture the worst performing area. So you can basically see now that this cable was a little bit worse than the memory I saved of the previous cable. But let's save that as well now and look into another cable, because I have a few more to go to. So now that we've done that, we can export those graphs into RBW Instrument View. So as previously, I will connect to that. And I'm simply going to click Get Trace. And now we can see the traces that we captured on a big screen. So in the measurement setup, it tells us all the parameters that we have selected, be it the center frequency, the span, the reference levels, as well as the range. And most importantly, we have our bandwidth settings, as well as the sweep time. I didn't go over the sweep time too much because most of the time we control it by setting the bandwidth, but essentially the sweep time is the sort of speed at which measurement is taken. I typically have it set to automatic, but you could also adjust it and see how it works for you the best. The trace capture window is not particularly informative, and you usually have to set it up on the Spectrum Analyzer first. So now let's look through the rest of USB cables that I brought here. So again, let's set the mode to max hold and have a look at the cable. So you can see now that this cable is much better, and it's giving us those kind of very low noise floor that we actually ideally looking for. So now we can get the trace again, and you can see just that the yellow trace, which is our latest cable, has got much lower noise flow at the frequencies between 280 to 400 megahertz, and overall the spikes are much lower, with maybe exception of this particular point here. So anyway, I have now generated 4 plots for different USB traces. Even though I can't combine them within Instrument View together, this is a bit of a limitation of this spectrum analyzer, as it can only plot 2 traces at a time. Still, I can analyze them and draw conclusions based on my observations to select the right cable for my product. And the USB cables are very important because it's your responsibility as a manufacturer to select the right cable that passes EMC. I hope you enjoyed the video. Please like and subscribe, and I'll try to publish more videos about the practical use of equipment for EMC testing really soon.